Hello and welcome to the Great Minds series. I'm super excited in this series. We have not one, but two exceptional guests. I'm delighted to welcome our first guest, Professor Karl Friston, a leading neuroscientist known for his groundbreaking work in brain imaging and his development of the free energy principle. On the other hand, Dr. Markus Müller, a physicist whose academic journey steeped in theoretical physics and mathematics. His work delved into the intriguing crossroads of information theory and quantum mechanics. Today, we are stepping into the realm of theoretical neuroscience and quantum mechanics as we dive into the physics of the first-person perspective.
Okay, thanks very much. So let me say in advance, thanks so much for your interest and your patience, your interest in all of this. Let me begin with a disclaimer. So what I talk about today is very speculative and probably to a large extent wrong. Yeah. It's also very abstract and counterintuitive. So that makes it a bit challenging for me to explain it and to depict what it has to say. What I can promise, though, is that it is a consistent approach. It's, I think, well motivated. If it's true, then it solves a couple of interesting questions. But if you believe, well, I don't possibly think that the world could be that crazy, then that's completely fine. Then you can just see it as like 1 hour of like fun science fiction, perhaps. Yeah. So indeed, I'm usually working on other things. Also some interesting overlap perhaps with Professor Friston's work on free energy, so in a very different context. Now what I'm talking about today is in some sense a very concrete proposal for a very different or unusual picture of the world, in which the first person comes first in some sense. But I should also say that this has almost nothing to say about concrete everyday questions, such as how concretely does the brain work, right? So it's also not a theory of everything or something like that, because it has nothing to say about most physics questions that we're interested in. Just to make this clear, here's a comparison. So suppose you're a proponent of general relativity, and then you bring forward this very, very popular thought experiment of an observer in an elevator. So there's this thought experiment that if you're in an elevator and you don't have windows to watch what's going on outside, you will never know whether you're floating in outer space or whether you're free falling on Earth, right? Now suppose that they bring you now together in a podcast with a very renowned biologist who's really an expert on the biological details of how the sense of balance works. Then it may be quite hard for you and the biologist to have a lot to say to each, say something to each other that would benefit the specific questions that you're asking. I feel a bit similar. So I feel like I don't really have anything concrete to say or directly to say about how the brain works, or what the neural correlates, for example, of consciousness are, or something like that. I also suspect that what I'm proposing, the abstract core of it, is manifestly indifferent to many of the specifics of how humans or other instances of observers just happen to be composed and what they look like, right? Like the specifics of the world that we happen to observe. Nonetheless, I'm looking forward to this discussion, so perhaps there is some common ground in the end. I definitely have to say that I find some of Karl Friston's ideas very interesting, so more on popular scientific level. So sometimes, when I read on blogs about trapped priors as explanations of some psychiatric conditions, also explained with free energy principle, and I find this very interesting, but it doesn't directly touch my work. Now, I have 3 things to say, basically. First is, why should we have a thing like this? How is it done in general, and what does it predict? But before going there, let me ask back, how much time I should take, or whether there are any questions or comments so far before I go to these questions.
You should take as long as you feel you need. For me, I'm looking forward to this. This is going to be a learning experience for me. Just to relax you a little bit. I spent the weekend reading about you. I had to read the proof of George Muser's new book, and he clearly spent some time in conversation with you. So I'm looking forward to hearing a summary of the ideas that you were discussing with George, as I'm sure the audience are. So you take as long as you want.
Okay, that's great. Thank you so much. Good. So as I've had 3 questions, why, how, and what does it tell you? So first, why? So what are the kinds of problems that this approach tries to solve? So consider the following question. The question is, what happens to me next? Or what should I expect to see next? Now, the goal of my approach is to try and give an in principle answer to these questions in all situations, including very exotic ones. So let me begin with a simple standard situation, like when I will ask, what will I see next? So suppose I go to the laboratory here at the Institute. I see a particular arrangement of mirrors and of lasers and other equipment on the table. And then what I can ask is, well, for example, should I expect to hear the detector click? Now, certainly I can use physics, in particular quantum theory, to compute a prediction, for example, a probability of hearing a detector click. So this is what we usually do in physics. This is like the standard methodology. We say we model the world or the relevant part of it and its evolution. Then we locate ourselves inside of it. And then we calculate what that kind of piece of matter is, what's happening to that, right? That's essentially what we do, even if we don't spell it out always. But then there are these exotic situations where this prescription doesn't quite work. For example, the computer simulation of agents. So somebody promises to scan you to whatever detail and simulate a copy on a computer, for example. What should you expect? Should you expect to make observations that correspond to the simulated agent or not? And perhaps you want to put a probability on that. I claim that physics is in principle silent about this question. And then there are these duplication scenarios put forward by philosophers like Parfit, which are something like these, Star Trek science fiction scenarios. You enter this teleporter, you dissolve, and then a copy gets built up on the planet where you want to travel. But then you might have a malfunction and suddenly you have 2 copies appear, or more than 2 copies with slightly different properties. How should you think of that? Say before it happens, it will happen. What should you expect to happen to you? In physics, in quantum theory in particular, there's a puzzle that appeared that's called Wigner's Friend, the Wigner's Friend paradox, which somewhat essentially asks how you should think of being put in superposition and whether what you predict to observe is somehow consistent with what other agents might predict to observe. Final example would be what's also appeared in physics, the Boltzmann brain problem. I will explain this a bit more broadly because I will get back to it. So this is in a nutshell, so I apologize to all the fellow cosmologists who know this much better than me, but the main idea is very simple. Suppose the universe is very large, perhaps your model predicts that, eternal inflation or some other model predicts that it's perhaps combinatorially large. And then just due to thermodynamic or quantum fluctuations, you know that a lot of stuff must just go on randomly out there. In particular, in some of these models, you expect that there are many copies of you just appear due to random chance, statistically. They would be perfect copies of you and your memories, but in the next moment, these copies would somehow make a very strange observations, like what the hell is going on, and then disappear. Yeah, that's a very colorful depiction. The cosmologists really want to think about this, because they might say, well, if your model predicts that, then maybe your model is sick and you want to rule it out. But again, the question appears, how should you think of that? In particular, if an observer in such a universe as we think perhaps, what should you expect in the next moment to happen to you? Usual planet business or strange fluctuation experience, right? It seems like in all these cases, the standard methodology does not directly apply. It's at least unclear how to use it. So you need something else. So that's the why. Yeah. I think it's just a worthwhile goal to try and have an approach that attacks these questions uniformly and says, here's a method how you can in principle work it out. Good. Now how could you do it perhaps? Well, how can you build now a theory that would allow you to do this? There are several options. Others, I'm not saying I've found the only one. It's not even a full theory, but the main idea is when you say, like, if I cannot apply this methodology, like here's the world, it evolves, here I am, then gets one step back. Let's get one step back and not talk about the world. Let's first talk about you, whatever makes you you. Right? So mathematically, you would want to say there's something like the observer state. So that's whatever it is that is you right now, basically a snapshot perhaps of, well, naively think of all the relevant content of your brain, including memories, observations, whatever will in the end define you. We would think that perhaps experience and consciousness and all that supervenes on that somehow, but that's not important for what I'm going to say, right? So your state doesn't have to be conscious or anything. So think of you during a surgery. It doesn't need to be human or biological. Think of just some pattern somewhere that causes what happens to that thing. Let's talk about the observer state in itself. And let's postulate a law that says, if you are in that particular observer state now, you will be subjectively in another state next with some probability. Yeah. Ideally, that's it. You just do that. You try to guess a well-motivated probability law, and then you work out the consequences and compare it to what we observe. Yeah. Now, certainly what you want for that to be successful, what you demand from this is that it should agree with the physical predictions in the standard situations, at least in principle, even though it's maybe hard to apply in practice. So, you want to see the situation where you go again to the laboratory at the institute with a description of lasers and mirrors, and your state, which includes all the memory and whatnot, things you're not aware of that make up you. You want to be able to prove that this approach in principle gives probabilistic predictions that are consistent with those that physics would give you. If that's the case, then you might trust the approach enough to apply it also in these exotic situations. That's the hope, and that's the goal. Now you can ask, well, but what could this probability law be? What would be a good choice? And then I think a good, well-motivated choice would be to use something like a reverse principle. So it's like the inverse of David Lewis' principle. And what it would say is that the actual chances that you postulate, what happens to you, what are the probabilities, they should coincide with the epistemic predictions of maximally rational predictors. So what does it mean, more concretely? Well, I suppose I'm given your state right now, whatever it is. I put it on the table. I cannot really do that, but suppose I give it to a team of scientists. They are very well funded. They have all the time in the world, and they look at this string of data. Right? Now, you can ask what they could probably do is they could work out that, that looks a bit like here, looks like a recording of some digital image. Maybe there seems to be a dump of some brain, of some being in a three-dimensional world. And here I can infer that stuff was moving in some ways. Just from the recorded data, you can puzzle together a lot of facts about the world where this came from. And then you can make a prediction and say, well, if that's the case, then this is what this guy should see next. Right? So this is a version of universal induction. And to formalize that, you can use algorithmic information theory. So algorithmic information theory is a part of information theory that gives you different options to formalize this in detail. What you end up with essentially is to say, my next state is more probable if it's more compressible given the current one. So in some sense, if the next state looks more business as usual or more like a natural continuation of the current one in a precise mathematical sense. Okay, so that's the main idea, what you would want to formalize. Yeah. Let me point out there are many options, how you could do it in detail. For example, also how you choose how to model observer states mathematically and so on. Right? But it's also very simple, and you want to stick to it and not postulate other things and see what things it can reproduce that we know about our world. So then if you do that, then what? So the last question is what does it actually predict or explain, perhaps? One thing you get is automatically, essentially, is you get consistency with physics in principle, assuming that some version of the Church-Turing thesis holds for our physical world. The Church-Turing thesis would tell you, for example, that if you build an experiment and you feed an exhaustive description of the experiment into a computer, the computer can calculate probabilities of future outcomes for you. So there's an algorithm in principle that you can use to predict. If this is the case, then you can prove that in the long run, the probability law that I've told you will coincide with the actual physical predictions. So that's consistency with physics. In this view, however, you are not fundamentally actually embedded into some physical world. Instead, the approach predicts that in the long run, your states will look as if you were embedded into some larger system. That system is computable by a short program on a probabilistic Turing machine. And you can now call this your external world if you want. So it tells you that there exists this model where you can imagine that you're part of that thing. So what the probabilities that you see are marginal probabilities of this larger process. And that would mechanistically explain what you see. So this is a sort of emergent notion of an external world. Importantly, this is not a theory of everything. So a priori, this approach predicts almost no properties of that world, except that it's computable, that it's probabilistic, and that has probably simple laws, even though the actual realizations of the data you see are probably complex. Now, this seems to be in agreement with what we see, but there's no claim that this could actually give you the laws of physics, or it would be a theory of everything of that sort. Now, at this point, you might also understand already how it solves the Boltzmann brain problem, or what it has to say about that. So again, let me rephrase it quickly. So suppose this world around you that you infer, that you think sits there and is consistent with your observations. Suppose that has that property that it's very large and that you should expect that there are many copies of you sitting around. Now, the first intuitive question as a human that you want to ask is, now, given all these copies, am I the real guy on this planet, or am I one of the copies? That's what you would want to ask intuitively. Now, my approach would tell you this is not even a meaningful question. So there's no property of you that would tell you you're one and not the others, right? You are just your observer state, your pattern, right? And that's the same pattern here and in the fluctuation out there. It's like the number 6 is just the number 6, whether it's these 6 eggs in the basket on my desk or whether it's the 6 soccer balls in the room of my little son. However, here's a second question that you can ask, and you can ask, well, good, maybe that doesn't make sense, but what should I expect in the next moment to see? Should I expect to see business as usual on Earth, or should I expect to see something strange that would happen to these fluctuations? And then the answer would be, yes, this is a meaningful question, and you should expect to see business as usual continue. Why is that? Well, that would give you observations that are more compressible given your previous state algorithmically. Okay, so this would also be bad news for the cosmologists. So in some sense, some cosmologists want to say, hey, fellow cosmologists, your model predicts so many Boltzmann brains, then it must be wrong because it's not consistent with our observations. But in my approach, you cannot do that, right? Even if there are many copies, the sheer number of the copies would not have any bearing on what you should expect to happen to you and on the chances of what will happen to you. Finally, this is like the most counterintuitive aspect of it. You do get an emergent notion of objectivity. And this is like the last thing before I finish my long monologue. And it's perhaps the most science fiction and fun part. Right, so here's what happens to me, right? So I have these observations, I'm in the state, and to me it looks very much if there was this world around me, and I can point at something over there. That thing, or that seems to me like another observer. This has carries a lot of data. I would call this Professor Karl Friston, right? And so I can predict that tomorrow there's an almost 100% chance that I will see Professor Friston see the sunrise, right? So I can work out the probability that I will see this other person see something. All I need for that are the laws of physics. It's like piece of matter that records data. Does it, like, do the camera eyes look at the sun? Yes or no? Good. Now you can ask, but what if you are actually Professor Friston? Right? So if you are that observer state that's represented in this data over there, you can also, like, my approach claims that then you should believe your chance of seeing the sunrise is just given by this universal induction probability, by algorithmic probability. And then you can prove a theorem that these two probabilities are very close to each other, as long as what I'm pointing to carries enough information and is complex enough. So this would tell me that my world is also Professor Friston's world. And that appears also to other things that I point to in my world, even if they are not biological, like the data on my hard drive, for example, or other things that carry a lot of data about the external world. It would not, however, apply to simpler things. And then we would have the notion where, you know, the notion of objectivity breaks down in some sense, and you get something I call the probabilistic zombie. So this would be situations where me seeing something, see something, has a different probability than that other thing actually sees something. And that's totally counterintuitive. And that's a novel, like, phenomenon that's predicted by approaches like mine. Good. So that was kind of a summary of my proposal. As I said, it's not a full theory yet. So I have the general idea, and perhaps you can see some of the ideas worked out and explain how they should work. I have a concrete model worked out, something like a bit model, where you just model the observer state as a string of bits that grows one bit every time that make a new observation. And there I can prove rigorously some of the things I claimed. But certainly actual observers forget something sometimes fundamentally. So that's why the rigorous version that I put forward in this paper here certainly does not apply yet. And there's a lot to be tried and improved, and you may try out different versions. You may also try to falsify it when you say, here are statistical predictions, perhaps too strong fluctuations expected on the laws of physics. We don't see them, then we can put the theory in the garbage can or so, right? So that's also something to be worked out. But yeah, I'll stop here. And thanks for listening for such a long time, for your attention.
Love it.
Dr. Muller, thank you very much. That was intriguing. There's so much that one could pursue there. I was intrigued by this notion of probabilistic zombies. So I'm probably going to ask you to unpack that a little bit more. But just to celebrate points of contact, I'm now pretending to be the biologist who knows how the sense of balance works, and trying to make sense of your more fundamental and foundational physics perspective. But having said that, a lot of what you said makes entire sense when viewed through the lens of at least a biomathematician. So I just wanted to sort of highlight the points of contact, which I understood, as a prelude to then going back and looking at some of the more outrageous or counterintuitive implications of the way that you're actually deploying this particular theory. So a whole bunch of consilient observations that come from your formulation. One way of reading your notion of the natural way to predict what will happen next in terms of the compressibility and the minimization of algorithmic complexity, that is something which I can completely subscribe to, or when I say somebody committed to understanding things in terms of the free energy principle would absolutely be there completely. And indeed, there are, I think, two routes to motivating or understanding the foundational role of, or two routes to understanding processes that look as if they're optimizing something, and the thing that they are optimizing is some variational bound on marginal likelihood or model evidence. And for me, that would be the variational free energy. And one route would be sort of the Richard Feynman route from quantum electrodynamics, and sort of thinking about how material things like you and me, from a biologist's point of view, would actually make sense of their sensory data in exactly the same way that Richard Feynman was trying to work out, how he could make sense of distributions of different small particles pursuing different paths and trying to, derive the probability distributions over those paths, which is an impossible marginalization problem or integration problem, but can be solved by converting it into an optimization problem. So now, if I'm solving the same kind of inference problems or perceptual measurement problems or observer problems, then if I use that kind of trick, I will certainly look as though I'm optimizing something, which is this bound on the free energy, and that would be, I think, the sort of the story or the narrative that people like David McKay and Geoffrey Hinton would use in terms of appealing to that pathical formulation as the genesis of free energy bounds, evidence lower bounds in machine learning. But there's another route, and I think it's probably one much closer to your formulation, which I fondly think of as the Russian route. So the fine would be the American route, but there's another that starts with algorithmic complexity and Kolmogorov, and via that right through Solonov induction and universal computation. Actually, interestingly picked up by people like David McKay in cryptoanalysis, that exactly the same maximization of marginal likelihood and the minimization of free energy. These things are exactly the same as basically representing things in a compressed fashion that minimize the algorithmic complexity. And interestingly, if you look at what current biologists, or certainly neurobiologists, like to think of as a way of implementing this compression, what it would look like in the brain, you'd end up with something called predictive coding, which I'm sure you're familiar with. And of course, predictive coding was, certainly in its linear form, was something that engineers invented in the 1950s to compress sound files to minimize the algorithmic complexity of the encoding of large sound files. So to my mind, there's a wonderful sort of, if you like, convergence on exactly the same quantity. And indeed, people like Jürgen Schmidhuber have been sort of, shouting about all you need is complexity minimization to explain everything for many, many years now. So I just wanted to emphasize this notion that there is, I think, a natural law out there that would be underwritten by a compression, a drive to efficiency, a probabilistic maximizing the efficiency of something that you had observed. If that thing you observed left its impression upon you and your state, that you were describing, all the states that constitute me and my brain and all my internal dynamics, then I think that the argument that natural law would rest upon this. You call it universal induction. Is that the phrase that you used?
Yes, I use this phrase. Yes.
Yeah. Is that related to universal computation then? Is as read by by the sort of people who inherit from either Solomov or indeed. Have you come across the work of Wallace from Melbourne, University in Australia.
So it is Solomonov's prior, by the way. I haven't come across Wallace's work. What's the first name?
I'm afraid I can't remember because he was always referred to as Professor Wallace. But I remember visiting Melbourne once, and they had a philosophy/maths group. So what Professor Wallace was basically their head of department and had died a few years prior to me visiting, but he was certainly outside Russia the real champion of this sort of algorithmic complexity view of stuff, self-organization through to efficient coding through to universal computation, and wrote some seminal papers that they were very proud of. So I always try and reference this gentleman, Professor. I hope I've got the name right. I'll email you afterwards in relation to that, because I think that the Australians felt that they'd been left out of the big arguments with the Canadians with Geoffrey Hinton and the like, and some of the Americans. But I just use him as another point of reference, that somebody outside Russia saw this as a fundamental way, a universal way of understanding computation or physics as computation or information processing, from the point of view of complexity. And just to bring this point of contact to closure, that literally underwrites, from the point of view of cryptanalysis, the kind of variational free energy that I mean when I talk about minimizing free energy. When I think about this, and certainly an explanation to students, when taking a perspective on variational free energy as an evidence bound in statistics, what I generally say is that you can just rewrite that marginal likelihood, or the variational free energy in physics would be the negative log of that marginal likelihood, as a linear mixture of the accuracy and the complexity, where the complexity is a Kullback-Leibler divergence between your prior and posterior, so before and after getting the observation. The impression of that observation on you, your observer state, can be scored in continuous formulation. So this would be appropriate for sort of continuous state space models, as the KL divergence between the prior and the posterior, so literally scoring probabilistically the degree to which that observation changed your mind. That fluctuation, how has it moved you from t to t plus 1, and that's the complexity. And of course, because the log evidence, or the log marginal likelihood, is equal to accuracy minus complexity, if you're trying to maximize, as every good statistician should, the evidence for her hypotheses, then you are going to try to maximize the accuracy of your account of this observation. But under the crucial constraint, you're trying to minimize the complexity. And it is that link, I think, which is fundamental, and sort of ties you to the universal induction and universal computation. That's the compression. So you don't want to change your mind too much, because if you change your mind and use up degrees of freedom, you're now incurring a complexity cost, which is exactly what you don't want to do. So I normally read that sort of Occam's razor aspect, which I think you could also read in terms of James's maximum entropy principle, or even Jeffrey's priors in statistics. I read that as basically getting the right priors to enable you to compress everything, so you don't need to move away from your priors. If you can compress this information and understand it and rewrite it, or explain it in terms of good priors you've already got, then your posterior doesn't move very much, and you've now got the most efficient compressed representation. I'm not sure about the maths, and I'm sure you'll be much more fluent at this than I am. I remember looking into it once and trying to use the law of large numbers to connect this statistical measure of complexity to the algorithmic complexity. But at least heuristically, I just look at these things as just two ways of looking at the same phenomena, one from the point of view of continuous state spaces, and one from the point of view of sort of discrete bits, or of the kind that you could apply algorithmic complexity to. Have you come across that sort of statistical complexity thing before?
Yes, indeed. So I'm glad you say this. So certainly a lot of what you say is corroborated by a couple of theorems that relate, for example, Kolmogorov complexity and entropy, or conditional Kolmogorov complexity and Kullback-Leibler divergence. So essentially, the expected value of Kolmogorov complexity is entropy. So this is why your intuition that you mentioned, like, how surprised am I by the new observation given the previous one, as measured by the Kullback-Leibler divergence, can be interpreted as some kind of expectation of the conditional algorithmic complexity, except certainly that you're in the continuous regime. So what I said is true for the discrete one, but surely this connection can be made. Right. And this is something I definitely find interesting, because I'm indeed looking at alternative ways to model observer states, right? To model probability distribution, in particular ones where I don't have to add a bit at a time. And now I wonder whether I should, study in more detail how you actually formalized it. I haven't enough, right? But yeah, go ahead.
Well, I would certainly encourage you to do that, because it is seldom the case that I meet somebody who is fluent in both the continuous sort of data analysis kind of computational complexity and the inherent information geometries of continuous state spaces. Things like Fisher's information metrics, right, and information geometry, and how that relates, and how thinking about this sort of complexity measure as a KL divergence, moving from your from your prior to your posterior, is literally a movement on a statistical manifold that has an information length whose metric is the Fisher information. So the whole bunch of beautiful maths, but it's all in continuous state spaces. If you could understand and become fluent in that to the extent you could join the dots with the pure algorithmic stuff, I think that would be a great service. I'm sure these are exactly the same stories, but written in a slightly different rhetoric from the point of view of different kind of mechanics. And I'm not sufficiently well versed in the algorithmic complexity and universal computation to really sort of say these are basically the same kind of story. If you could do that, I think that would be very, very useful, and you'd make a lot of friends, or at least allow people to sort of see each other's perspective. So I just really encourage that if it can be done, and don't forget to cite this Australian gentleman Wallace.
All right. Yes.
If I've got
that. Professor, is it Chris or Mark? There is two. One of it is called Chris Wallace. He's into information science. Could be him?
That doesn't ring. He used to be at I'm pretty sure it's Monash University in Melbourne.
It's Mark Wallace, I think.
Mark Wallace. It's
right.
Mark Wallace. Yeah.
Right. Yeah, and he would have been writing, I think, in the sort of 80s and late 90s, if I remember correctly. So I'll do my research. I'll send you my favourite citations, that sort of capture the essence of the things that we've been talking about.
That is really interesting, and I thank you so much for pointing me to this. I do have a somewhat question for you of technical curiosity. So, are there results that say something like, if the environment, if the world is of that and that kind, then I obtain a guarantee that the free energy minimization will be successful for survival, for example? So I guess, so for algorithmic complexity, for example, it would be a version of Church-Turing's thesis. So you need some in-principle computability. But probably you would also be able to say something about, for the statistical version, like probably the environment shouldn't be too unpredictable in principle or something like this.
I see. Yes, I'm afraid that there isn't, and I'm probably not the best person to ask, basically, because my background is more sort of intuitive physics and
Yes,
biomathematics. But there are certainly a lot of notions that would speak to that basic outcome, that if you are embedded in some meaningful way, but individuated from a particular environment, external milieu, some niche, then there would have to be a non-equilibrium steady state exchange between you and the observer and the thing generating observations. I know you may not like that because your whole thesis is there's nothing generating observations, but in my world, you've got to be slightly less philosophical about it. You assume that there is some world there, and you've got some observer, and they are individuated in some well-defined sense, so that the observations that are doing the updating is in the direction of being maximally compressible or minimally complex under the constraint of it still providing a good representation or accurate explanation for. Just open brackets. If you could show the equivalence, you've also now got a duality with James's maximum entropy principle. If you read the maximum entropy about of the probabilistic description of what caused your measurement, your observation, so that the constraint just is one way of reading this is that the constraint is supplied by, or at least scored by, the accuracy of your measurements. It's you'd have to move certain terms around, but put simply, the free energy formalism can also be read a la James, in the sense that you've got an entropy of some belief distribution encoded by your observer states that has to be maximized in the spirit of Occam's razor. You don't want to commit to a particular explanation, so it has to be simple in the sense it has to be liberal and non-committal, but you've got a constraint, and that constraint can be written down in terms of Lagrangians or Lagrangian multipliers, or specifically from the point of view of the free energy principle, a negative log probability of particular observations, and indeed the external states causing them. Sorry, I'm just adding a little bit of momentum to my encouragement to you to actually join all of these dots, because if you can join it to the free energy principle, the statistical, the Bayesian statisticians' use of variational free energy as as an objective function to get good models of things, to make sense in the best kind of way of observations, you've also got an easy point of connection with maximum entropy and maximum caliper principles from James as well. So you could tie everything together. But sorry, to come back to your question, so in that respect, then you can, in fact, the answer to your question really is the raison d'etre of the free energy principle, that if you have a system that is in some characteristic states, and that system, say the observer, can be separated from the thing that's providing the observations, then just by the existence either of a non-equilibrium steady state and open exchange, so these are all about open systems, then just by either the existence of that non-equilibrium steady state solution, or the existence of dynamics at any for a suitably long period of time, then you can always explain the change in the state of the observer in continuous state space formulations as a gradient flow on the variational free energy that has this complexity computational complexity part of it. So the answer is yes, possibly the other way around. If you are in non-equilibrium steady state exchange with your environment, another way of reading that would be, if you had evinced some kind of generalized synchronization of chaos, if you want to put sort of random fluctuations in play, then there will always be a description of your next state or your current dynamics as a gradient flow on the same quantity that hopefully we share a commitment to, that has this sort of compressibility aspect to it, there's an efficiency aspect to it. So that's certainly true. Early versions of that, which would be another nice thing to sort of draw into the fold of things that are all, if you like, pointing in the same direction, inherit some cybernetics. So this is the work of people like Ross Ashby and Collett. So things like the good regulator theorem and the law of requisite variety could in one sense be read as answers to your question. So have you come across those early notions?
No, I'm not at all familiar with this.
Oh, you'd like that. And he also was able to prove stuff. I tried to read the papers. I never really understood the proofs. But I think you would like this. So this is circa probably 1950s, possibly later 70s. But certainly the early work of people like Ross Ashby. So the good regulator theorem just says that any observer that it lives in a controllable world must be a model of that world. And the law of requisite variety can also be read as the degrees of freedom of the observer state must be at least those have a cardinality of the environment that is being controlled. So again, this notion of being, and it's a notion I think was implicit in your opening comments about, where should I look next? So it's all about actively controlling, not controlling, but engaging with a world. So you're open to something that you're observing. So you can control your observations by, where do I look, over here, over there? So from the point of view of the good regulator theorem, is assuming, or they were assuming, that there is an observer. There are things out there that could be controlled. The observer doesn't know, necessarily need to know the structure or what those things are. They just needs to have enough degrees of freedom on the inside, the internal bulk, to match those things that can be controlled out there. And then it is provably the case that if you have this open exchange with the world, then the internal dynamics, the observer states, must be readable as, or be a good model of the of what's going on out there. And it may be that the proofs do actually sort of portend the later derivations that eventually, several decades later, led to the universal computation and, as I understand it, universal induction. But you'd have to go back to, I think, to that very early literature. So that would be one other way of saying that, if I exist in a world and I can observe that world under the caveat, I have to control the way that I solicit those observations. I have to actually, have some reciprocal exchange with that world. Then yes, there can be no other solution to that than me being a good model of that world. And of course, what does being a good model mean? Well, it means I've got a compressed representation of the causes of my sensations. And what does that mean if I'm, in universal time? Well, it just means that my states will be those that maximize the model evidence in a continuous formulation. What's model evidence? It's exactly what we were saying before. It's a thing that's bounded. It is just the mixture of the accuracy and the complexity. So I think it all does fit together. I repeat, it would be interesting if I remember the proofs of the good regulator theorem, although they may be a little bit heuristic for your tastes, given the formalisms that ensued, they may have been articulated in the kind of language which you would recognise. There's certainly some elemental Shannon-esque information theoretic.
Yes, indeed. I'm actually intrigued by your description. I should say, in many cases, what I used are theorems that, as theorems, can be read either way. So that could be applied, like thought of being applied in situations where I think of an observer that is actually embedded in a fundamental way, or use the theorem and turn it around and use it in my approach. So to get one step back, I'm just interested in this, for like what you can prove there in generality. And what you said intrigued me, because this good regulator theorem, when you say, well, the observer has to have enough degrees of freedom for the world somehow, the observer states must contain a good model for the world in order to have the ensuing sustainability of that observer. That's mathematically really similar to my condition for not being a probabilistic zombie. That's essentially the same condition. So the observer state must contain enough information about the part of the external world that affects them. And if so, then it's not a probabilistic zombie, and then the probabilistic predictions that you would put forward if you just describe that world would match the probabilistic predictions that you would get if you applied it directly to the observer state. So I'm intrigued by these proposals because they seem to point at some very deep mathematical underpinnings that perhaps can then also be used to make a more conceptual relation to this more statistical approach that you're working with. I definitely want to pursue this. So I thank you already for pointing me to this.
Yeah. And we've happily got back to the probabilistic zombie. So that was a bit clear. Could you just speak more about that was intriguing, the probabilistic zombie.
Yes. So in my approach, the notion of objective reality is not assumed and built into the formalism as you would typically do, but it's the content of a theorem that you prove, right? And certainly every theorem has its premises, and it is in that premises you get that conclusion. And the premise of this theorem has to do with that other thing that you're pointing to, that you interpret as another observer, containing enough information about your world, right? So you can quantify this in terms of Kolmogorov complexity, essentially. And of the world, I really mean essentially the laws and not the actual realization. So somehow when I point at your brain and I think that we have objective descriptions. So what I think my probabilistic predictions of what happens to you should agree with yours. Then this has to do with, in my approach, with saying, well, the Kolmogorov complexity of your state is much larger, essentially, than the Kolmogorov complexity of the laws of the world that affect you in the regime where you live. Just the laws, not the actual data of the air molecules or so that would be of high complexity, but the laws by which they move, essentially. So intuitively, I would say that this applies to certainly all other things we would intuitively call observers. It doesn't apply to things that are point to that have very small information content. Right? And it also applies in situations where, so how should I say, so like computer simulation of agents. So you can simulate a simulated being in a simulated world on a computer may have large information about its simulated world, but not about ours, about our world. That's why in my approach, essentially, it's the simulated world that's effective for that simulated being. Right? And so, for example, if you depict that simulated being in a world where beings just happen to suffer, then you shouldn't feel guilty because you're not causing that. Right? So that's a bit the idea. But as soon as you start talking to the simulated being, like, and you feed in some data and say, look, you're actually in a simulation. Here's some photographs of our galaxies, and that's what our laws look like, and so on. Then you would at some point overwhelm its observer state with enough information about our outside world so that whatever we decide to do in our world becomes causally effective for its subjective transitions. And then you should feel guilty at some point. Yeah. So I'm very vague and quick here, and it sounds a bit crazy, but that's somewhat the predictions that you get. Right? So probabilistic zombie, again, to summarize, would be a thing where it would have different probabilities when you were that thing as compared to how I would see that thing evolve. This would be different probabilities. And that's counterintuitive, because I think that even in thought experience, like if you think of like the many worlds interpretation of quantum mechanics or other extreme situations that you think of, we typically don't think about it in that along these lines. So because that would be a bit strange. Maybe to finish this one other thought experiment that I had with George Musser recently. So we had a couple of emails exchanged, and I tried to explain the main idea, but not sure how well it went. It's a bit the idea again of computer simulation. So in the future, you buy a lot of computing time, and then you simulate on your computer a simulated universe, right? According to simple laws. You have lots of compute, so you have like evolution starting in your simulation, and some evolved being comes up and asks about the meaning of it all and what's going on, and finds perhaps by experimentation the laws of its simulated world. And now you go ahead and say, well, you intervene in the simulation, or you change its laws immediately. Perhaps, you change something dramatically that's kind of on the sky, far away from the simulated being. And then at some point, that simulated person wakes up and sees in the newspapers that NASA does, like, astronomers can't believe it. Suddenly the sky has changed in some regime of the universe. What the hell is going on, right? Now, that would have a very strange description in an approach like mine. Because in my approach, you can think about the simulated being before reading the newspaper, just as long as the simulation is going as usual according to its laws. They would say, well, fair enough. If you were that simulated being, then what you would see is also what we as from the outside would see, right? So you in your simulation, you would see the simulated sunrise. And if you were that simulate, like that observer state that's represented by a simulation, you would actually also see the sunrise. But at that moment, when you change the laws drastically, these probabilities would diverge. If you were that observer state that was simulated, you would probably see the old laws just continue, right? So whereas you looking at your simulation where you intervened, you would observe a simulated being with high probability that has actually experienced the change of laws and seen that. So one very colorful, intuitive way to interpret this would be to say, well, somehow the person has leaked out of the simulation, and he's been replaced by a kind of unlikely changeling somehow. Now you have this other thing that you simulate, and you can ask about what would it be like to be that thing, right? But that would be somewhat a separate question of asking it for this observer state before the change. So you'd have these very strange and very counterintuitive phenomena of kind of, persons falling out of their universes or so, like, which are hard to visualize, I think. But it wouldn't happen to you and me because we're not probabilistic zombies relative to each other.
Well, yeah, but of course, with all the current excitement about large language models and giant AI, in terms of AI alignment and the ethics of having large generative models, say generative AI in silico, I think I'm just wondering whether some of these arguments are actually practically and morally, in a philosophical sense, quite prescient, given current sort of focus on, say, regulation. How expressive, how big can these generative AIs come, and to what extent does their training correspond to receiving observations and trying to make sense of those in a Bayes optimal way, using the principles of universal computation. And of course, this is all in silico, usually on a Van Neumann architecture. So I do think there is practically the possibility of these probabilistic zombies, where there's perhaps I should rephrase what I have in mind from my perspective as a modeler and a modeler of modelers, i.e. other people. So I can certainly describe my brain, or indeed my family, in terms of it looks as if they are maximizing the evidence for the models of their sensed world. And then I can try and create a little artifact, a little synthetic person. And we do this quite a lot in a very, very elemental way, just to simulate toy games and economics games and psychophysics experiments, with the aim of trying to fiddle with the parameters, usually of the prior beliefs of the observers. You talk about the laws and the contingencies, they're normally written down in terms of priors, in terms of generative models, and we build these little synthetic agents to adjust the priors until their response to an experimental paradigm matches that of a patient or a subject, just to try and get a digital twin in the computer, which you can then now start to ask, well, what would happen if I gave them this synthetic drug, or change this connection, or to try and understand the sense making implicit in these. So there is a very practical, if you like, instance of probabilistic zombies that people are actually using in computational neuropsychiatry, for example, actually at hand. And one can see another interesting example of this is the Virtual Brain Project, that's come under used to be in the auspices of the Human Brain Project, and now eBrains. And the whole point of that is to create digital twins of people with epilepsy, so that you can ask, if I did this surgery to relieve this intractable epilepsy, what would happen before you actually do it on the actual patient. So there are people out there building probabilistic zombies, and the reason they're probabilistic zombies, perhaps not the virtual brain, because that just tries to reproduce neuronal like biophysical dynamics, but some of the agents that we build actually we install in them generative models, prior beliefs of a probabilistic sort, that provide the constraints we were talking about before, that underwrites their constrained maximum entropy principle. So that we are, unlike me trying to describe a member of my family, so I can see how the member of my family behaves. I can look at the dynamics, and I can reverse engineer the kind of observer model that was, if you like, underwriting their dynamics. From your point of view, that universal induction being an expression of some Lyapunov function. For you, it could be sort of an algorithmic complexity. But you would need to, I think, at the end of the day, write down the model, or what you were trying to compress. From my point of view, if I was trying to understand a member of my family, another real sentient artifact, I would be reverse engineering their model, their understanding of the world, how they were compressing their observations. But when I simulate an agent, I'm doing the other thing. I'm doing it in reverse. I'm writing down a generative model, and then just using the gradient flows and the updates on t to t plus 1, under the assumption that they are going to minimize their complexity, for example. And this has a name. It's called the ideal Bayesian observer assumption. So when you go into biology, you always commit to something called the ideal Bayesian observer assumption, which is just that your belief updating in your subject, simulated or observed, is going to comply with universal computation. It's going to be Bayes optimal from the point of view of a Bayesian statistician. But of course, because you've given it the generative model, which has got nothing to do with the real world, you've created a probabilistic zombie. And as you say, it's the model that you've created, you're supplying that, if you like, that objective function, that Lyapunov function, to generate in continuous time the dynamics that you're trying to simulate in a real person, in this digital twin, for example. Because you're supplying that model, it's got nothing to do with what that model actually sees, or it's got nothing to do with the world out there. It's just appropriate for the kinds of inputs and observation supplied by that particular model. So I think this notion is it's not just, if you like, philosophical. A philosophical nicety or an interesting thought experiment. I think it could actually have real implications. When you tell your digital twin, in fact, you're a digital twin, then they have to do all sorts of belief updating should they want to. But you said something quite interesting. You said that the digital twin, say my digital twin and a computer, they would just carry on observing, and because the way I read it was, because they had no way of updating and being able to predict this random fluctuation in the sky, in this part of the sky was bright orange, for example, they wouldn't be able to see it. And I'd certainly concur with that. You can't perceive, you can't see, you can't represent, you can't compress, you can't register anything that's not part of your internal repertoire, your model of the world. So they wouldn't be able to see what was going on, even if the person presenting the big orange blob in the sky in silico or in the simulation was able to see what the agent was seeing. Is that what you meant by this dissociation now between the observer and the observer of the observer?
I am also wondering a bit. So maybe it's actually a bit different. So it's nice that you think that there might be actual applications of such an approach in these scenarios. Let me say where I see a potential, and then let's see if that's also what you had in mind. So I suspect that it's a bit different still. So I think one question that you may want to ask at some point is my language model, is my simulated agent, maybe you simulate a bunch of neurons at some point, is somebody at home, right? So you may want to ask, have I created consciousness? That's the way we typically tend to phrase it, I think. Now, we usually think, well, this question is not a question. This is essentially a question of the philosophy of mind. So you would have to somehow understand, what does consciousness mean, make a theory of that, and then try to apply it to that specific structure that's sitting in your computer or so. Whereas if something like my approach is true, then there's a level below, and that's like asking, is there, if you were that thing, would this be coherent with what the simulation shows? Right? So, and then the answer turns out to be sometimes no, which also in particular implies that there's nobody at home in the way that you would intuitively think for consciousness, right? Even though you didn't say anything about consciousness. But the idea is that, so not being at home here would be, so we tend to say, like, here's something I can point to, something spatially localized, perhaps a piece of matter or a particular localized pattern in my simulation. And it makes sense to ask, what's that thing feeling, or what would it be like to be that thing? In some sense, my approach denies that. It rather says that if you are if you are you, whatever that means, then you are a pattern, right? It will often look as if you were spatially localized and instantiated on some small material part of a larger process, like part of a computer simulation or a piece of matter in the world as we think of it. But that's not fundamentally the case. And since that's not fundamentally the case, you can have a divergence between these two. Right? You will not have a divergence. It will just be the same thing when in the usual situations, like, in our world, we point at stuff that has high complexity, or we run a simulation with constant laws, point at a persistent pattern there. There being that pattern is the same, like makes the same probabilistic predictions as we would describe what happens to that pattern. But what I described is extremely counterintuitive. You would have a divergence of these probabilities without being able to point at a mechanistic cause of the divergence. So if you're the simulator, you're running your simulation, you're changing the laws immediately, then in principle, there's nothing for you that you can misunderstand. Yeah, you see what the simulation is doing, right? It's running according to these laws and then the others. You see what the simulated being is doing and saying and claiming to see. You'll see them watch the newspaper and being surprised suddenly something's going very weird, and then it sometimes gets used to it after a couple of times. You can perfectly understand that. But when you ask, if I were that thing in the simulation shortly before the change happens, what are the chances of what happens to me? Yeah. Then these chances are given by the probabilities of the old laws. Right. So, and that's an information theoretic reason, essentially. Right? It's not, so when I said intuitively, this is something like the simulated being falls out of the simulation, then I don't have a mechanistic story to tell, like something kicked him and he really fell out of it in a mechanistic way. No, it was more that the abstract law that predicts what observers see tells you that, right? And it's just a derived prediction that the first and the third person perspective typically agree. So that if I'm the simulator and then I see what my simulated being is experiencing, that's what it will actually experience. So the divergence is not mechanistic in the sense, it's structural and surprising, in the sense very counterintuitive. So what you were hinting at, I think, was also for me very interesting to learn what you do there. But it seemed that you were able to tell a clear story about what happens in that simulation of the, like, say, of your family members, of this little agents that have reduced structure, that you want to predict how your family members would respond to treatment. You could still say, according to the mechanism of the simulation, I can understand this kind of divergence between the simulated family members and your actual ones. Whereas I think this would be a different mechanism, a different kind of thing. Yeah. Does that answer your question? Does that make sense?
Nearly. It's still, the counterintuitive and the magic aspect of this is what's intriguing me here. So this notion of being knocked out of the universe, that I found quite intriguing. So are you saying then that the simulated observer, from its point of view, in the face of some designed or large fluctuation, which was completely unpredictable, so there's no way that the normal sort of ideal observer rules apply. There's no way that you can call upon universal induction to properly respond to or make sense of this large fluctuation. Are you saying then that from the point of view of the observer, that observer just disappears, gets knocked? What happens to this poor observer that's seen something that's never seen before in its life and cannot predict and cannot perceive?
Yes. So first note the similarity perhaps to the Boltzmann brain problem and the way that I try to the solution is, proposed here. Somehow there you also say, well, you would expect business on planet as usual to persist, regardless of how many copies are out there. Right? Why is that? Well, essentially because you are your state, and it's the same state here as in the copies. So you shouldn't think of you as sitting either here or there, right? You're somehow all of that at once. And now this kind of colorful interpretation also applies to the simulation. Yeah, you say, let's interpret this for the moment. It's not part of my theory, but let's interpret this as a kind of many worlds picture. Yeah, you can think of all possible worlds. One of them is like the world with laws as it evolves, like in the beginning of the simulation, unchanged forever. Another world is the simulated world with the change of laws. Like there are many other possible worlds where essentially a copy of the very same observer state would appear. Now, the idea is that you are not actually the thing in the simulation, but you're somehow all of these copies at once. Right? It's more like, it's just that some of these instantiations have higher statistical weight than others. And those that have higher statistical weight are those with a simpler world, essentially. Right? So that would be a kind of many worlds picture, if you want, of why algorithmic complexity or probability would apply here. So then in this picture, you wouldn't really say that you're kicked out of the universe. It's just like, usually, you would think that you're that thing in that regular universe, because that regular universe has higher weight, and you're not actually the other one in the more complex universe with changing laws. Right? Now, if you're the simulator and you look at your simulation after changing the laws, you will certainly see a simulated being in some observer state. I'm not claiming that this is now a zombie in Chalmers sense or so. No. I mean, you could also think of what it would be like to be that thing. It's just when you've been that other thing before, then that would be a very rare place to end up later, right? So it's very weird. So maybe, when you have the simulation and maybe you made friends, you think emotionally attached to the simulated being that you had running around there, like, and you think like, oh, I want really that my friend is well off in the future. I don't want to hurt the simulated being and so on. And suppose you want this at the moment before you change the simulation, right? You want that being to be well off. But you also know that the being is very unhappy when it sees a drastic change, right? Maybe that's the personality of the simulated being. It wants to be in a predictable environment, right? But you're now forced to change your laws. Should you be worried? Well, in some sense, no, because with high probability, your friend will continue to see regular laws, right? It just will be elsewhere. You'll then see another being, one that has actually seen changed laws, and you may make friends with them. And then you may be unhappy that other thing is unhappy. but it's a bit, it's even less intuitive than Everettians want to paint the world, I think. But it's consistent.
Yeah, I mean, the many worlds way of framing it, I think helps. Yeah, I think. Okay. Yes. I'll have to think about that a bit more. I think I'd have to do that with a cigarette and just think about that. Just one practical point. I have a lot of friends at the moment in philosophy of consciousness, and they are asking. Very much like people talk about the neuronal correlates of consciousness. Are there any computational correlates of consciousness? It strikes me you're in quite a good position to address that, through the lens of a physicist. And one argument that has come to the fore, interestingly, is can you simulate consciousness? You almost implies that one way of looking at these surprising or counterintuitive outcomes under the application of this universal inductive approach did speak to, is there anybody home, in the simulation. One interesting thing that's come out of that is that it might matter. Just taking, coming back to a conversation we were having before about the generalized synchronization that ensues when you're in some open or non-equilibrium steady state in exchange with your world as it's going on predictably in the right kind of way. It might matter whether you're doing your simulation on a von Neumann architecture as opposed to not in-memory processing or processing memory. I think what Geoffrey Hinton refers to as mortal computation. So that the actual physics of the observer state and the dynamics and the thing that actually has the complexity is, if you like, doing the computation, as opposed to simulating the computation and reading and writing all the laws into memory on a von Neumann architecture, thereby violating, if you like, or abandoning Landauer's bound on the. So I should just qualify that for the viewers and our other friends here. That one way of looking at that sort of stepwise change in compression or universal induction or the movement of a belief structure with each new observation is you have to erase information to change your mind, and erasing information needs a particular amount of thermodynamic work, and there's a lower bound on that, or an equivalent that is known from physics, but that only applies when the thing that's changing its mind is the actual thing itself. So this is what I was hoping that Geoffrey Hinton meant by mortal computation. That's not what happens in a simulation machine. It's not what happens in the Matrix. It could be what happens in a brain in a vat if you're talking to a good old-fashioned philosopher, but it's not what happens in the Matrix, where you've actually got to read and write from memory, which takes orders of magnitude more energy just to bring stuff out. So I was just wondering whether it's a slightly practical thing, but if you now commit to the thermodynamic consequences of your interpretation in a literal sense via things like the Janinski equality and Landauer's principle, can you ever really have anybody there, even in a simulation, if your simulation is not mortal, in the sense that it's not using a von Neumann architecture?
This is a fascinating question. I really like this question because it kind of opens up the question, like, what if you change your model, say you make it probabilistic instead of homograph complexity, like which features survive and which change? And in particular, this question, like, is the implementation important about how you do the computation, for example? I take it, I just discussed here with Kevin McQueen about IIT and what they assume and what not, like integrated information theory. We had a long discussion because they seem to insist that the arrangement and the actual physical realization does matter, whether you can call that thing conscious or not. Whereas I thought intuitively, I don't believe that, right? I think it shouldn't be. It should just be about the pattern itself. Now, two things about that. The first thing to say is the way I formulated it now, the pattern, like the way you implement it, doesn't matter. It's a matter of degree, essentially. I come to that perhaps later, but the second thing to say is that I like the question that you posed, because you may ask now, if that's my conclusion for this specific model with the bits and so on, what if I change it? Will it then be more dependent on its thermodynamic realization and so on? This is an intriguing question. I agree. To say how it's at the moment in the way I formulated it, there, I would say, in principle, every simulation is just a depiction of an existing structure. You're not bringing things into existence, unless you intervene somehow. So let's think about a simulation where I talk to the simulated being or make some decisions and some interventions and so on. And then the complexity of your simulated being is not just the complexity of that pattern, or yes, it is, but when you ask whether being that thing is the same as being in our simulation in that world, yeah, then you have to take the complexity of its description given our world, which includes the location function. So how do I pick out that structure from my world, right? I have to say where it sits and what kind of computation I have to do to read it out of the computer. And if that computation is too complex, for example, if the simulation is running in a very encrypted, delocalized way, then the readout function might be so complex, yeah, that in total, this world with the simulation has very low statistical weight for that being, right? And that it's not actually contained in the simulation. So there's some sort of degree to which, like, how you do your computation. You shouldn't make it too contrived and delocalized and so on. Yeah, that's, I think, how it's at the moment.
Are you happy with that, Professor Friston?
Yes, I am. Yes. So we've been talking for a long time now, so you'll have to stop us talking at the point.
Yes, 90 minutes, because there is 10 audience on the stage. It's waiting patiently to ask you both questions. So, Professor Friston, are you happy and satisfied with the questions, or do you need more time?
Oh, we could talk for hours, but no, I think we've covered all of our favorite issues. Thank you very much.
Let me thank you, Professor Friston, for all your time, and it was a lot of fun to talk to you about this. So thank you so much.
It is. Thank you so much. So we're going to open up the floor quickly. I have a question, but it's not exactly a question. I think both of you have addressed it briefly. I'm just having a bone to pick. So recently there's an article about Christof Koch losing a 25 years battle on understanding the neurological basis of consciousness. It seems like even with the wine on the line, consciousness remains, an enigma wrapped in the brain scan. So I just wondered, how do you both perceive the interplay of consciousness and the physical world, especially when it comes to the integrated information theory and global neuronal workplace theory, for instance? So, Dr. Muller, could a deeper understanding of the physics of the first-person perspective help unravel this mystery at all?
Article that you just mentioned, I would just in general say that we should do all we can to study the neural correlates of consciousness with all methods of neuroscience that we have. It's just from the other side, from the philosophy side, I see many arguments that there may be very hard problems remaining. Like there's what Chalmers called the pretty hard problem. I think that we may solve one day with neuroscience. The hard problem, I think, we'll need neuroscience and philosophy. It will probably need less physics than the physicists would want to believe, but that's just my personal guess as like a non-expert.
Thank you. Professor Friston, what about your thought about that paper?
I haven't read these. Could you send me a link to the paper afterwards? It sounds very interesting. So I haven't seen that.
Yeah.
I want
lost a 25 years bet. Yeah. To David Chalmers.
Yeah.
Yes.
This is Christof Koch, is it?
Yes, it is.
Yeah. We share the same hero. So both Christof and myself have a hero called Sherlock Holmes, a great detective from London. Is a fictional character. That's one thing we share in common, and a common friendship with Giulio Tononi, who was the architect of IIT, Integrated Information Theory. But I wanted to disagree with Markus. I think we will need physicists to solve this, to be quite honest. And I think it is in the direction of universal computation and these universal laws that basically dissolve any bright lines between information and energy that are going to be at the heart of it. I also think that IAT is certainly on the right track, but it's missing something which Markus has brought to the table, which is the fact that there's a difference between the observer and the observed. Until you think seriously about the relationship and the distinction between the observer and the observed and the implicit relational aspects, and I use the relational as a nod to people like Carlo Rovelli and relational quantum mechanics. I don't think there's going to, I'm not sure you're going to get a satisfactory answer about consciousness. There has to be something fundamental about the observer, the measurer, the inferrer, and the relationship between that which is being measured and observed and inferred before I think we're going to get any get seriously close to a philosophical resolution of the hard problem. That would be my position. I don't know if Markus wants to push back on this pro-physicist. I still have physics envy, you see, which he probably doesn't have.
I will not attack the physics profession now.
Let's not. So we're going to move on. Thank you so much for that. John, have you got a question, John?
No, I think I'm out of my league here. I'm going to leave it to people on the stage.
Okay, thank you, John. I'm going to quickly move on. We're going to Adam.
Thank you. I was wondering about the connections to the principle of least action. If I understand what you're saying, Dr. Muller, that this principle of universal induction is what's determining, is what stands in for, physical laws, and the connection that Dr. Friston, you're making to the free energy minimization. I understand these things in a very rudimentary way, but somehow I feel there's a connection to the principle of least action. I wonder if you might comment on that.
So should I start perhaps? Because your idea sounds somewhat familiar to something as a PhD student, I wondered about this as well, and thought, like, certainly you minimize the action to get the laws of equations of motion and mechanics. Can you understand this as a kind of complexity minimization, which is the story you tell from the other direction of thermodynamics and computation and so on? In the end, my intermediate result or conclusion was perhaps, but maybe not that directly as I thought. So the way I like to think about the principle of least action is really in the architecture of the world. Somewhat you need a couple of steps to get there, and one step below is, I think, quantum mechanics and the path integral. And when you do an approximation of that, which gives you classical physics, you end up that you have to minimize the action. And once you have something like quantum states, there are information theoretic reasons for understanding where the path integral comes from, for example. And once you're there, you can get to the principle of least action. So the way to, the place to look would probably be information theoretic derivations and underpinnings of quantum theory and the path integral. Right? But I think a direct connection, we say maybe action is just complexity among this and that measure, and not the other one out of this complexity. So I don't think that can be made that easily.
Thank you. Professor Friston?
For me, there is a direct link with the principle of least action. I mean, we often say that the free energy principle is just a variational principle of least action, and the action in this instance is just a path integral or a time integral of this bound on marginal likelihood or negative log marginal likelihood. So the free energy principle, everything that entails, is a variational principle of least action. I'm just thinking about Markus's answer. So we certainly use the path integral formulation. In fact, the most current and in fact the original formulations of the free energy principle drew upon the path integral formulation. You'd certainly need to use that in contemporary applications of the of the free energy principle, but you don't need the quantum mechanics, but you do need the probability distribution. So the way you get the probability densities into play is by associating the continuous internal bulk of the observer states where you are in some continuous observer phase space with a sufficient statistics or probability distributions. And once you do that, you're back in a world of which can be cast as quantum information theory if you and some people have tried to do this, but you don't need to do that. You can still work with classical information, but now you've basically got back into the world of probability densities by associating the internal states with parameterizing or represent a probabilistic description of the causes of your observations. And if you do that, then you've got you can read the free energy principle simply as a variational principle of least action. I still submit that, in the limiting case of the information encoded by bit strings algorithmically, where you can sort of, in the limiting case, put delta functions on things, and using the laws of large numbers, I'm fondly hoping you can get from that continuous density dynamics that the free energy principle employs to universal induction. So if Professor Muller can write the paper showing that they're effectively the same things, he can then say, and yes, this is also a principle of least action.
Yes, thank you. For a wonderful discussion. My question is a kind of context-based. If you have an observer in the first-person perspective, is there something it is contrasted against, like an experiencer state? And I ask that because I think eventually the observer and the experiencer, let's say in quotes, are, information systems. They contain some information. And like, what Professor Friston said, the observer state, phase state refers to the least action principle coming from free energy. So I'm wondering if any one of you, both of you, can talk a little bit about this kind of what the observer is observing with reference to these kind of attributes, right? Some kind of information based. And is there a kind of, can you think of a kind of a database kind of metaphor, something relational versus object oriented? I just want you to kind of philosophize, because I think a lot of people in the audience would love to hear that aspect.
I want Markus to go first.
Okay.
I'm even less of a philosopher than he is.
No, I'm not sure. But the answer will certainly depend on the framework. And I feel like I would have to think about it, but let me say what I understood, or what intuitively came to my mind when I heard your question. So the way I think of the observer state is just everything that makes up the observer at a single moment in time, which is, for you perhaps, not the chair over there, but it's also not just your experiences. It's also memories, including ones that you're not currently thinking about. Maybe also some aspects that you will never able to even think about consciously in the future. So the point is, the way I formulated my approach, you can apply it and make predictions and try to understand these puzzles without answering the question, what, say, for me and you, this observer state actually is, and how I should interpret it, and where in the state sits, experience versus memory or something like that. It's an extremely abstract level. It just says somehow, basically it says whatever this observer state means as a bit string. There's no dictionary that you can open and this is now the experience and these zeros and ones are the memory. It's more abstract than that. The meaning of that state is in its relation to other possible bit strings and the computability structure it's given to you by information theory, essentially. So this is power. You can do a lot with it when it's that abstract, but it also limits the possibility to answer more concrete questions, including your question. I don't know the answer to it.
Thank you, Markus. Professor Friston.
Yeah. So, in contrast, the sort of the classical FEP as opposed to the quantum FEP formulations would actually commit to the notion that the observer state, written as all the inside of something, a particle or a person, did encode beliefs, probabilistic beliefs about what caused the thing that's being observed, which means that there is a thermodynamic or a physical instantiation and implementation of the representation and the information, as it were, about something, and the thing it is about is what caused the observations. Of course, you'll never know what caused your observations, but you can have beliefs and fantasies about those. And it is this kind of representation, if you like, or explanation, to which the complexity minimization applies. That you have the least complex, the simplest, most parsimonious, efficient probabilistic explanation for the causes of your sensations. So I've introduced the word sensation because, I mean, when we talk about an observer state, one could actually mean the state of the internal aspects or state, say, of a brain or a thermostat that is responding to the observations, the sensations, which would be the thermoreceptor or the my eyes and my sensory epithelia. So I think there's another delicate set of questions and answers to be had about what does an observer state constitute? Is it the bulk that's on the inside, or is it the bulk that's on the inside and the observations that are impressing themselves or represent the way of some putative world talking to the observer? I put it like that because there's an interesting talking about sort of quantum physics and trying to get us away from philosophy. There's an interesting map between, or relationship between, the thing that separates my brain from its lived world, which are my sensory organs, my sensory epithelia, my skin, my eyes and the like, and the notion of a holographic screen in quantum information theory. So another way of, if you like, looking at this sort of the way that the observer state is fundamentally separated from what is being observed is to think that think of it in terms of the separation. In my world, that would be, in a classical world, that would be a Markov blanket that has these sensory impressions upon it. But in a quantum physics or quantum information theory, not quantum physics, but quantum information theoretic, this would be a holographic screen that divides the bulk of one system, which could be an observer, from another system that is being observed, but they can only talk to each other by reading and writing from the screen itself. And on that view, one has to ask, is the observer state the bulk of the observer, or are you allowed to include usually classical information on the holographic screen? And if you can, or if you can't, more interestingly, of course, anybody, we've spent a lot of time talking about watching my computer simulation. I noticed that, Marcus's eyes lit up with all the counterintuitive, exciting implications once we started talking about me looking at another observer. But of course, if you've got this holographic principle in play, you'll never really know what's going on in the thing you're observing. So it will always be as if, because there's all you can see of your simulated person, or indeed your loved one, is what is projected onto that holographic screen. You'll never ever get beyond it. The only way you can communicate, certainly with classical information at least, is through that. So it wasn't a good answer, but the experience, I'm assuming then, is an attribute of the inside, the bulk on the inside. The observation is the thing that may live on the Markov blanket or the holographic screen, which is your window on the world, and possibly that world will contain other observers, but that will just be your fantasy.
Yes, thank you, for both of you for the wonderful interpretation of that. I have a follow-up question for Professor Friston, because you have in-depth understanding of the psychiatric side of that same thing. So how do you embed the concept of an observer phase, state, space, stability? Is there do you see some kind of link to the psychological aspect of our interpretation of the world and ourselves, especially our identity? I'm just wondering if you can, take us through that for a few minutes. Thank you.
Right. I feel selfish using a few minutes. I think we've only got 11 minutes left, but very briefly. That's a great question. And indeed, it is why we committed so much time to investing in the sort of the physics of sense making and belief updating, simply because in psychiatry and psychology, it's all about beliefs. And certainly in psychiatry, it's when beliefs are slightly aberrant in relation to the thing that's generating the consequences, or the things you have beliefs about. And I think you're absolutely right that a very important aspect of my compressed representation of the world is the representation of me as an actor in that world. So you don't have to, a thermostat doesn't have to have a sense of self. But if I have to engage with other observers, it's coming back to this theme, which was recurrent in the conversation with Professor Muller, which was observers of observers. If I live in a world that's full of other observers like me, then I'm going to have a model of a good regulator-like model of a good representation, a compressed representation of what it is like to be an observer, including myself. So I'm going to have self models. Those models are going to be compressed. And another way of reading the right kind of compression is having the right priors. If you remember before, the statistical view of compressibility is putting the priors in the right place, so you don't have to move away from them to have a good explanation for what's going on, including me and how I behave in this situation and how I relate to this other observer. So people do come along with very, very different priors. And in a sense, you could possibly read all neurology and psychiatry as people presenting with priors that are not quite fit for purpose in their world. And very often they're held with undue precision or conviction, which means that they're very difficult to shift. So, quite literally, they are stuck in a rut, but it's a rut of sense making and self-modeling and universal induction. And then you normally end up asking, what are the biophysical ways in which we represent that the precision of, or the commitment to, or the confidence in certain representations or beliefs. And then there's another story about how that might be leveraged from the point of view of pharma and psychotherapy.
With the cybernetic and AI ecology currently building in the world today, how do you anticipate that this will change the subjective observation experience of the individual? People used to be able to navigate using maps, but today rely on smartphones with GPS technology, and younger people may have lost the skill to navigate using a map. How will this technology impact the subjective experience of observing?
As an amateur and not an expert on AI, it's a question that I also find really exciting. Like, how will AI change my everyday life and that of my children in the next 5 years, 10 years, 30 years? It's very hard to make a concrete prediction. Like, for me especially, I'm not an expert, but also when I try to follow the experts who also seem to disagree very much, I personally tend to be optimistic. So when you talked about navigation, so fact is, I was very bad at navigating and finding my way before smartphones. Now I'm much better, even when I turn it off, because I feel like when I have it and I make my way for the first time, I see the map and I memorize it, I get a better understanding, and then I can do even better without smartphone. So for me, it's kind of a win-win thing. It's not that I got worse with it, I got better with it. I like to hope that something similar will happen with other aspects of us and AI, that, for example, we can have personalized teachers, perhaps, that tell us in our own best ways of understanding, teach us about whatever we want to know and what have to learn. So basically, I'm personally optimistic, but it's not, I'm not an expert. It's really just a personal feeling.
And I'm no expert either, but I'm equally optimistic. I don't really subscribe to these dystopian views of what might happen if artificial intelligence or our augmented ability to download certain cognitive capacities into the environment, to use a sort of the perspective of Andy Clark. I don't really see that. I have this more utopian view of things. I'll just give you one example. I do acknowledge that certain skills will be lost in children, basic arithmetic, for example. But there are other skills that they're gaining. I'm too old now, which is why I asked Markus to answer first, as a proper millennial, I imagine. But I'm too old, and I don't have a mobile phone. I'm too old to use them, because they're too small. And I remember being on the tube about 10 years ago when everybody, apart from me, was doing, the metro, the underground train.
The underground, yes.
The underground. Everybody had their smartphones out, apart from me. So I could just watch everybody else observing their smartphones. And what really struck me was children who were able to type using both thumbs at an incredible speed. I mean, almost at the speed of an insect. I couldn't physically do. So yes, they will probably be completely unable to ever repeat their times table, but they had such magical motor fluency with their thumbs and their ability. That was a new skill, which, you wouldn't have found 30 years ago, and you certainly won't find in my generation. So I'm sure it's all going to be okay, but things will change in terms of our competences and the way that we relate to our world and our e-world.
So I'm just going to go with the train of motion from Prakash's series of questions. And I was just wondering if the two of you could touch on, there are a couple of terms that help with this observation, and it's called metacognition or meta-awareness. So I was wondering if one of you or the both of you would like to touch upon like metacognition or meta-awareness. Quick example, if I was reading a page in a book and say, what happens to some people is they keep on reading, but they lose attention, and they're not processing actually the contents that they're reading consciously. But there are people that apparently are aware of when this mind-wandering episode occurs, and the ability apparently is meta-awareness, and this can be cultivated in one's life. So I was just wondering if, and it works with memory, right, as well, and that's why I'm really happy that you brought up not only just the experience, but the memory aspect. So if one of you would like to touch on metacognition or meta, that'd be great. And thank you both very, very much.
I mean, I know nothing about this. Perhaps Professor Friston knows.
I know lots about this because I've got lots of friends who do metacognition. It's a really important thing. I have to say that Professor Muller does know a lot about this because he was talking about observing the observer quite a lot here. so he may not know.
That's exactly why I thought of it. Sorry to interrupt, but you are absolutely correct, and that's exactly what triggered the question within my observation.
And I think it's very relevant. I mean, I'm aware that we're out of time now, but I think it's an excellent question because not only do we there's a whole science of observing others and observing the observer and dyadic interactions and theory of mind that speaks to things like autism and the like. But of course, we are our own observer, and we can observe ourselves. So as soon as you have that capacity to decompose in some hierarchical way, as in, say, hierarchical theory of mind or higher order thought theory, approaches to metacognition, then not only do you have the question of, what's it like to observe an observer, but what happens if that observer happens to be me? And I think you get into really deep and interesting questions of a metacognitive sort. Just to highlight how important that is, a very sense of self, I think, rests upon that metacognitive ability. A thermostat, and one could argue possibly a bee, and even small pets do not need to know that they are a sentient thing in order to operate very, very efficiently as having a basic kind of sentience and an observation. But when it comes to very sophisticated creatures like ourselves that have to engage with other things that are equally sophisticated, it matters whether I can contextualize and infer whether you cause that or whether I cause that. And I now need a sense of self in order to have that exchange and to observe an observer that's actually observing me. I think at that level, you can see how easily things can go wrong. If you don't get these, if you don't have the right kind of self model. And again, we come back to the potential applications to psychiatry, and you could argue in some instances neurology as well. So, great question.
Thank you. Both of you have given a lot of material for us to chew on for some time. So my question is very simple. As free agents, the observers as free agents, do they have free will? I'd like to know quick reactions from both of you.
Yes, they have free will from my point of view, absolutely. And in fact, from where Professor Muller started, where am I going to look next? I mean, you have to select where to look next. If you have to do that selection, it's only you can do that because you're the only observer of your universe, then you have to have free will.
I agree. Yes, you have free will. So I'm a compatibilist. I like to read Daniel Dennett, written one paper about how information theory can understand your compatibilism perhaps a bit. So long story short, yes, I think we have free will. Yeah.
Yeah. Hi. Thanks. This is fantastic. The thing that piqued my interest was when you mentioned the emergence of objectivity, and it was an interesting turn of phrase, I thought. And then you went on and you talked about it as like the convergence of probabilities, I think, when you were talking about the sunrises and stuff, and sort of like if an observer calculates a probability and somebody who's observing that observer calculates the probability and they converge, then that is in some sense building objectivity. So I guess, or something like that. First of all, did I hear that right? And later you went on and said that you don't assume objectivity, but you get it as a theorem, I think is what you said. So I guess I'm really curious about that. Does that, is there any dependencies there? Like, does it emerge in time or like in scale, like spatial scale, or does it depend on like the amount of information? Like when you get a certain number of bits, things converge. And is that this convergence? Is that like a special condition, or is it like a generic thing? Like, and then could there be special conditions where it diverges and there's like critical points where things go awry and you don't have objectivity? Or I'm just really curious about that whole thing. I'm curious if you can riff on that a bit.
Yes, that's a great question. Thank you for it. So the main mathematical background of having such a theorem has to do with something a bit different, but perhaps more well-known, and that's known as Bayesian coherence. So that would describe a situation not in my approach, but just in the usual way that we think the world works, where you have two agents that are immersed in, say, the same environment, and that hold different prior beliefs about the world. And now they go along and, make more and more observations. And then under some conditions, you can prove that the priors will essentially converge to the correct distributions, if you want, or towards each other. So the different versions, mathematical formulations of that, known as Bayesian coherence, also available, some versions are in quantum theory. right? The interpretation of this would really be just epistemic about knowledge. Like say, here's a guy with beliefs, another person with beliefs. The more they learn, the more they agree. And you cannot agree to disagree ultimately. So that's what will happen. In what I'm doing, you don't have that available. So you don't have a joint environment into which you would be fundamentally actually immersed. Still, like the mathematical reason why I get such a theorem is essentially the same. And then from the usual formulation, you can kind of learn what is important there. It's not so much the scale, like how large the observer is, or the matter, or the time. It's more the amount of information that they hold. So the idea is that you, as an observer, observe this emergent world, and that's something that's predicted by this approach with a certain probability. So suppose that's the case, then you point at something, some structure in your world, yeah? And that evolves in time as well. And that's what allows you to compare probabilities. Your probability of how that thing evolves versus the probability if you were that thing, right? And the probabilities are close if the information content of the thing that you pointed to is large, right? So that's essentially, again, the criterion of that not being a probabilistic zombie. So that's what I called earlier. So essentially, the information content of what you're pointing to, of the other observer, must be larger than the complexity of the probabilistic laws that governs its the relevant features of the world. So the more, so it's like asymptotically, it's in the limit, the theorem tells you, in the limit of learning infinitely much information, your third person probabilities and that thing's first person probabilities will converge towards each other.
That sounds very much like a sort of metacognitive, or perhaps Bayesian coherence version of the law of requisite variety, where the variety is just the degrees of freedom available to hold that information
That's, I have to look that up. I don't even know what that is. I make lots of notes here and stuff to read up for me. This is great.
It's from the same stable of cyberneticists that did the good regulator theorem, but it subsequently developed into the law of requisite variety, which is just having enough degrees of freedom in the thing you're pointing at, that is commensurate with the informational complexity of the thing that's doing the pointing, I imagine. Anyway, that's your job. I don't want to spend waste anybody's time, because that was a great answer. It hits you in the face when you certainly model communication. So when the thing you're observing is actually being generated by another observer, like you, then very, very quickly this sort of requirement that neither of you can be probabilistic zombies, and you actually have to evince that generalized synchronization. So I am the cause of your observations, and your observations are the cause of my observation, or you are the cause of my observations. You get some really nice mathematical image of the ensuing Bayesian coherence and the convergence on a synchronization manifold, to use the jargon of generalized synchrony. That it is just that. I just asked Professor Muller, would this be akin to a principle of unitarity and entanglement in quantum physics, that everything basically ultimately coheres? Is that the idea?
Maybe it's the opposite in a way. So we have Howard Wiseman here visit and talk about Wigner's friend, in fact, where the whole puzzle comes from unitarity. You have the friend in the box and Wigner on the outside. Wigner describes the box and the friend unitarily. The friend describes it as a measurement. So in a way, there you would have a situation where you specifically don't have the communication, and then you don't know what to do. Then you wouldn't have consistency of viewpoints, and you don't know what to say. So that goes a bit back to your earlier comment, to which I wholeheartedly agree. So as soon as you have communication between two agents, then this kind of gets rid of zombie status, right? And you have to have synchronization somehow of your probabilities, either in an epistemic way, as you would usually interpret it, or in my approach, really as chances of what happens to you.
Hi, Markus. So see, this whole concept of observer is very interesting. So my own insight is that the observer cannot be modeled, whereas the observer state is, I think, what you're talking about. But the observer itself cannot be modeled because of the very nature of observer. Just as, for example, the taste and other things are a model of reality, but of course, scientists may say that it is like the content of the chemical action in the brain or something like that. But that is just an equivalence. As an experience, it exists independently. In that sense, like the observer exists independently in reality. It seems like. I just wanted to get your views. But if you do consider that observer cannot be modeled and it's not a thing, because if it was a thing, even that would be observed, basically. That's the point. And it always, the moment you try to observe it, then the observer has gone back, meaning like you try to model something and it has gone prior to that state, basically. So in that sense, it forever remains independent of whatever you try to do. So these are some of my insights. And of course, we have a totally different philosophy based on it called Advaita and other things, just for information. So you are very much, actually modeling, assuming this type of reality, it seems like to me. And I'm quite fascinated with it. And I'm going to study more in more detail, actually.
Okay, thank you. I should quickly answer to that. I'm probably running out of time, but just briefly. So thanks for the question. Indeed, you're pointing perhaps at two different things, like two aspects of it. One is like difference between observer states and observer. This is something that's common not only to my approach, but also to other philosophical questions about personal identity, in splitting scenarios, in aberrating many worlds, and so on. The teletransportation paradox, where one person becomes two or so. Turns out that in these situations, you cannot meaningfully talk about a person and identity of persons in a way that we used to in language, right? So that's one observation. The other question that you're touching at is just the distinction between the way we model things mathematically and what we think we really are. Right. So my claim here is, in some sense, we're more like a pattern rather than a piece of matter. But even when we talk about these observer states as some pattern, you can ask, am I the pattern, or is the pattern describing what I am, or how should I think of this relation and this isomorphism? And fortunately, I'm ultimately a physicist and don't have to answer because I cannot. I think this is a deep philosophical general question, I would guess.
Thank you, both of you, for being here today. And it has been a wonderful, wonderful discussion, and it's a lot to unpack today, Professor Friston. I will send you the link of Christof, the 25 years. The article will send you after the podcast. So this is it, gentlemen. Thank you so much. And it's brilliant to have both of you on. I would like to extend a thank. Can everybody unmute your mic and wish thanks before both gentlemen leaving the stage? Can you all unmute and say thank you, please?
Thank you. Thank you, both of you.
Thank you very much.
Thank you so much.
It was a great
Thank
session.
you.
Pleasure.
Yes, thanks.
A couple of Sherlocks up there. Thank you so much.
Lovely to see you all again, and thanks for the conversation, Markus. That was wonderful. Bye-bye then.
Carl,
Thank you. I hope both of
Have a good
you
night.
enjoy it as much as we do. Thank
Yes, we do.
you.
Bye-bye.